This is lesson 4.3 on graphs of inverse functions. So in the last lesson, we introduced this idea of inverse functions when we're talking about one-to-one functions. One of the ways that we mentioned that we could think about these inverse functions is if we consider the graph of the original one-to-one function. The inverse function is going to swap places with all the x's and the y's. So for each point on the graph of the original function, the inverse function is going to have the exact opposite point in some sense. So for example, if 3, 4 were a point on the original graph, then 4, 3 would be a point on the inverse. So the x's and the y's trade places. Another way that we can think about this is a reflection about the line y equals x. So when we reflect something about the line y equals x, we're doing exactly that. We're making every point switch their x and their y values. So what we're doing today is we're going to be looking at graphs of original one-to-one functions and then quickly sketch the graph of the corresponding inverse function using this property. We're going to reflect the original graph about the line y equals x. We're also going to look at yet another type of problem for the application problem where we are given the rule of a function, the rule of a one-to-one function, and we have to find the rule for the inverse function, but with the additional step of wanting to find the domain and range of both functions. We've worked a little bit before with finding the domain of a function when we're just given the rule, but up to this point the only really easy way for us to find the range of a function would be to look at its graph. And today we'll look at a special case of where when we are dealing with a one-to-one function and its inverse, we can very quickly determine both the domains and ranges of both functions without any idea of what the graph looks like. Alright, so let's consider this problem. So find the graph of y equals the inverse of f of x given the graph of y equals f of x. So the graph that we will be given is a one-to-one function. It's the graph of the one-to-one function f. We want to find its inverse. So we said before that the inverse is going to flip-flop. It's going to change the roles of x's and y's. So what we're going to do is we're going to sketch in the line y equals x. So the very first thing, go ahead and just write on the original graph itself. This is the graph of y equals x. Okay. Now what I recommend doing is look at where this graph crosses that line, if it does that. If it doesn't do that, we're not out of luck, but it's a little bit easier to see what's going on if it is. So some of us are going to be able to eyeball this. Some of us are going to be able to say, all right, this is going to go like this, and this will go like that. So there, ta-da, it's a reflection. It's symmetric about this line. If you could visualize what this looks like, if you could take this graph, pick it up, fold it along that dashed line, it would fit right on top of itself. Some of us can see that and do that. Some of us need a little bit more guidance. So let's think about this a different way. Okay, so notice here, what we need to do is we need to think of not in terms of am I going to the left or the right or up or down. Think of I'm moving in the positive x direction, I'm moving in the negative y direction. Think in those terms. All right, so notice here, my graph kind of starts along some point on the negative x-axis. The inverse function is going to change the roles of x and y, so my graph is going to begin somewhere along the negative y-axis. So let me go ahead and make some point right here. It's going to begin along the negative y-axis. So it moves in the positive x-axis, the positive x direction, while it's moving in the positive y direction just a little bit. So it's moving in the positive x direction quite a bit. That means this graph is going to be moving in the positive y direction quite a bit. So we're going to make a similar shape moving in the positive y direction, looking something kind of like that. It does not need to be perfect, just a ballpark sketch. Give me the right idea. So look at the graph, think about what's going on in regards to x's and y's, So go ahead and sketch this on the original graph, and then for your final answer, go ahead and recreate just the inverse itself. So there we go. This is going to be our final answer. So once again, don't worry. It takes a little bit of time to develop a better knack for this. If your graph crosses this line y equals x, we're going to intersect at that point. So that's another little extra tidbit you can use to help you sketch this. It does not need to be perfect. Once again, it does not need to be perfect. Just give a general idea. I recommend always draw your first go at it on the same graph as the original function. That way it's a little bit easier to visualize, all right, are these two graphs symmetric about this dashed line that I drew? If so, then great, you did it correctly. Copy down what you've written for your answer. If not, erase it, fiddle with it a little bit, see if you can figure out what you need to change to make it look better. Once again, it's helpful to think about not in terms of left and right or up and down, but moving in the x and y direction in the positive or negative direction. So here we said that we're moving in the positive x direction, which means here we're going to be moving the positive y direction. We'll give another shot at a different graph next. So here's another one. So sketch the graph of the inverse function given the graph of the original function. So just like before, the first thing we're going to do is put in our line y equals x, just to help us see how we're going to reflect this. So there is y equals x. Okay, now one thing to note that's helpful here. If we can recognize the general shape of our original graph, that will help us give the correct shape to the inverse. This we recognize hopefully as one of our x cubed graphs. So notice down here, our graph crosses the y-axis at about, oh, I don't know, just eyeballing it. Since we don't have tick marks, it's kind of an arbitrary scale. I'm going to say that's maybe, I don't know, 0, -2. Well, for the inverse, remember the x and the y values trade places. So that means this point here is going to become, it's going to move from 0, -2 to -2, 0. So let me go ahead and make a little mark right here just to help me see, okay, I know that my graph is going to go through that. Okay, from this point, notice that I move in the, as I moved in the negative y direction, I have a negative x value. So from this point, as I move in the negative x direction, my x value becomes negative. So flip-flop it. As I move in the negative x direction, my y value becomes negative. So I know that my graph for the inverse is going to look something like this. And check it out. Try to think it in your mind. If I folded the graph along this line, this little bit should fit right on top of this bit. They're going to match up perfectly. All right, now similarly, here, as I move in the positive y direction, my x value gets positive. So moving in the positive y direction, y value is positive, flip-flop it. As I move in the positive x direction, my y value is positive. So it's going to look like this. Once again, if your graph crosses that line y equals x, make sure that your inverse crosses it there too. So think about it, double check this. Think in your mind, if I could take this graph and fold it along the line y equals x, is this going to fit right on top of each other? And I think in this case, we can see that yes, we've done this correctly. They fit right on top of each other. So for our final answer, let's go ahead and recreate the red graph that we've done here. It's going to look something kind of like this to that. So once again, ballpark idea. The thing that I want you to emphasize here is that this is the mirror image of the original graph about this line y equals x. So let's consider a little bit different problem from what we saw in the last section. So up to this part right here, if you were to read the problem up to this point, this looks exactly like one of our drill problems from the last section. And the good news is it's going to work out exactly like one of the drill questions, drill problems from the last section, up to this point. This part, though, that's different. This is new. We haven't talked about this before. So that's the bad news. It is different. The good news is it's very simple. we mentioned before that we are accustomed to finding the domain of a function, but finding its range usually takes a little bit more work. We are going to use the fact that when we're working with a function, a one-to-one function and its inverse, the fact that the x and y values get switched everywhere to help us figure out the domain and range for both functions. It actually winds up being much less work than it sounds. But first, let's do the first part of the problem. Let's find the inverse function and worry about the domain and range once we get done with that. So remember, the very first thing we do, we're going to rewrite the original function as y equals 3x plus 2. Oh, big eraser. 3x plus 2 over 2 minus x. We switch the roles of x and y. All the y's become x's, all the x's become y's. And we solve for y. So I'm going to multiply both sides by 2 minus y. So x times 2 minus y equals 3y plus 2. And from here it's simple algebra. 2x minus xy, 3y plus 2. I want to get all of my y's together. It's going to move my xy over here. So 2x minus 2 equals 3y plus xy. So see, I move my negative 2 to the left-hand side and my negative xy to the right-hand side. I'm now going to factor out this y. So I have y times 3 plus x. Nothing changes on the other side. And then finally, I divide by this 3 plus x. So I have 2x minus 2 over 3 plus x. So there's my y value. So my inverse function, therefore, is going to be 2x minus 2 over 3 plus x. Okay, so we're halfway through. We have found the inverse function, but we still need to find the domain and range of both of these guys. So we need to find the domain of the original, the range of the original, and the domain of the inverse and the range of the inverse. Alright, so as I mentioned before, we're a little bit more capable of handling the domain. Remember, the domain of a function, when we're given the rule here, it's going to be everything except where things go wrong. The two big no-nos, again, are dividing by 0 and taking the square root of a negative number. We're taking no square roots here, so the only way that the original function can go wrong is if x equals 2. So for the original function, we want to make sure that x does not equal 2. So let's write that in interval notation. Everything except x equals 2 in interval notation, we write this way, remember. Negative infinity to 2, union 2 to infinity. Okay, not too bad. That makes a little bit of sense. All right, next, we know the domain of our inverse function. It's going to be where everywhere except where the bottom is 0. So everywhere except where x equals negative 3. So once again, let's write this in interval notation. So we're going to go from negative infinity to negative 3, skip over negative 3, and take everything else. Okay, so we've done the easy part of the problem. Or have we? This was pretty easy. The range turns out even easier. Again, remember, between a function and its inverse, the x and the y values trade places. So guess what? The domain is the collection of all of our x values. That means that in the inverse, this is the collection of our y values. So the range of the inverse is going to be the domain of the original. So the range of the inverse is negative infinity to 2, union 2 to infinity. And similarly, our x values from the inverse are the y values of the original function. So the range of our original function It's going to be negative infinity to negative 3, union negative 3 to infinity. So this last little part of the problem, it looks a little bit intimidating. It's not. It's quite simple. This part, not too bad. We need to be able to do this quickly because they're going to show up on our drill problems. This part is actually quite simple as well. We just need to remember our basic techniques for finding the domain of a function, find the domain of the original function, find the domain of the inverse function, and then we're essentially done. Things just swap places. The x values in the original become the y values in the inverse, and the x values in the inverse become the y values of the original. So this is meant to be more of a do you remember how to do this? There's nothing too terribly difficult here. Just remember this simple fact. When we go from an original function to its inverse, the x and the y values trade places. If you can remember that, we can find the domain and range of both functions very quickly, very easily.